Hello, everybody. Thanks for joining this next step and discussion, continuing the panel upgrade and electrification discussion with Brennan Less. Brennan is a researcher in the residential building group and splits his time between air quality and energy efficiency. And he'll have a lot to say about electrification and upgrades in residential setting. Brennan, take it away.
All right, thank you, Marco. And thanks to everyone for joining. I'm going to be building off of some of the content that I think Alex was just talking about around the challenges to household electrification that we see in sort of, our household electrical infrastructure, right? Like our panels and our wiring and our branch circuits. Today I'm talking kind of on behalf of the residential team at LBL. Many have contributed to some of the content in here, including Ian Walker and Daniel Gerber, and so I just want to give some quick credit to them. But yeah, thanks for your attention today. I think Alex already covered this a little bit, but I wanted to start off by just acknowledging that, based on current data, household electrical panels seem to be very underloaded, right, relative to their sort of like safe carrying capacity. We've gathered peak demand data from about 12,000 US dwellings. They're from, Vermont, New York, California, a handful of other locations. And when we look at the maximum that these dwellings ever use, and then we make, sort of a further conservative adjustment required by the electrical code, we find that, the sort of like typical home in the US looks like it's using half of its panel capacity if it had a 100 amp panel. If it has a 200 amp panel, that is, even a lower number. So we've got a lot of available amperage potentially for adding new loads to homes, right? In general, that the sort of like vertical yellow line here is the 100 amp reference point. The vertical red line is the 200 amp reference point. And we just see that very few homes really ever use that full capacity. And so this is very encouraging, right? Lots of opportunity for electrifying is what this says to us. And again, I apologize if there's like repetition from what Alex was just presenting here, and yet, like if you were in a home and you're trying to do upgrades, like you come to a panel that looks like this, and we're trying to add a heat pump, and we're trying to add electric vehicle charging, maybe we want to integrate, other power sources, right? Whether it's like a backup generator or solar PV or battery systems, and we look at this panel and it's like, where's the physical space, right? How do we fit it in here? Like, do we have amperage? Like maybe our load calculations suggest that we don't, right? Even though we just saw based on metering data that there should be a lot of available capacity. Like we're going to run into these issues, potentially quite a lot, and we need some solutions. I think Alex just covered a bunch of them. Part of the goal in today's talk will be to cover look into the future just a little bit to some other ideas. First, I want to like present some preliminary, please don't cite this, results assessing like, what is the actual prevalence of those problems, right? Like whether we have like a physical space constraint or an electrical sort of like amperage capacity constraint. What's the prevalence when we look across the US housing stock? Here we're showing, again, sort of a preliminary analysis based on res stock that we've done between LBNL and NREL out there in Colorado, where they represent the whole residential housing stock, and we sort of predict what panels are in those homes. We do load calculations. We make predictions based on sort of machine learning models for what the available breaker slots might be. And then, we're trying to figure out, like, if we did sort of a business as usual electrification, including vehicle charging, and we use sort of the current electrical code, how prevalent are these challenges going to be? And, here we're sort of showing like the fraction of homes in each state that has either a physical space or amperage, limitation. And the results, they look pretty bad, right? It looks like, with the exception of Florida, we have like roughly 2/3 of homes that have one or both of these constraints, ranging all the way up to the very low sort of 90% of dwellings estimated in parts of the upper Midwest. Minnesota looks to be like a particularly challenging case here. And so, this just, gives us a sense of the scope of this problem. It seems like it's like even in homes that have 200 amp panels or that are built more recently, we still run into some of these challenges. Is sort of what these preliminary results are starting to show us. And so what do we do about this? Like Alex covered a bunch of sort of like currently available ideas, but we still need more advances in technology, right? Those are going to be like communicating and, battery integrated appliances, load controls, the ability to do, load shedding, load shifting, modulation, all these sorts of ideas where we can sort of like manage our capacity. And part of that is, managing the actual demand of a dwelling and making sure that it, doesn't exceed safety thresholds. Um, and then the other part of it is just, sort of like getting an acceptable load calculation based on our electrical code, right? Where, the meter data seems to show that like in most homes, we probably have no issue and have plenty of spare capacity for adding new loads. And yet, we very well might get load calculations from the NEC that say, nope, actually this is, potentially a problem. So we need sort of these solutions that can both solve the like actual demand of the home problem and the sort of like, let's say, perceived demand of the home problem, which is, what we get in some of the electrical code. And so I'll spend a few minutes here talking about some emerging technologies that I'm hoping Alex didn't already touch on too much, and then covering some sort of like code innovations based on the code change process for the 2026 electrical code that our team's been pretty heavily involved in. So, what one tool that is sort of emerging, has been on the market for a little while already, are sort of meter socket adapters. And these, initially I think were out there for solar PV interconnection in cases where, we didn't have room to connect through the bus bar in an electrical panel. In some jurisdictions in California, it's called a green meter adapter, and every utility sort of has its own regulations around when they permit you to use this sort of approach and where. But the main idea is that rather than connecting a load or a power source into the panel, which might have space constraints or capacity constraints, maybe we can do a connection that is actually right up there at the meter, right? So we totally stay out of the panel. We make a connection by, connecting to the service wires at the meter. And what this does is lets us get around some of the issues that we have in homes with smaller panels, right? The NEC, for example, limits the amount of solar or battery power that you could feed into a panel based on the rating of the bus bar and the main breaker of that panel. This lets you get around that, right? So you're normally limited to add something like 20% of the rating. So for, a 100 amp panel, that would be like a, 20 amp solar PV system. Not very sufficient, right? In most cases, that's a lot smaller than we would put in most houses. So these kind of solutions let us get around that. Again, initially it was really just for solar, but like we're starting to see advancement where their products are on the market where we're going to not only integrate, energy sources, but also demand, right? So where maybe we could connect an electric vehicle charger through this method rather than through the panel, right? That's product that's getting launched in 2024 from Connector. And then we're starting to see, in the future, islanding sort of potential here, right? Where in power outages, we're able to completely sever the connection to the utility grid, keep the line workers safe, and still potentially power the home that's downstream of this sort of interconnection. So these meter socket adapters are kind of like a quickly changing and fast emerging thing. Again, they've been on the market for a while for PV interconnection, but we're, heading to having more flexible opportunities there. Another option for integrating renewables is sort of balcony solar. And again, this is another idea where we're trying to avoid being in the panel, like connecting through the panel. And what we see in Europe and in Germany, there's 500,000 of these units already, is that we get balcony solar that plugs directly into a household receptacle, sort of as a power limited, maybe 800-watt total output. And then that feeds into the house wiring and can service the other loads without sort of a battery and without a panel interconnection. Currently, this is not permitted in the US. Like we have, utility and regulatory safety concerns around feeding power in The issue is like, are we protecting our line workers, in the event of a power outage, for example? So this is an interesting topic that lets us potentially have sort of like plug-in, portable, DIY sort of solar power. But there's a lot of sort of like regulatory code and standards work that would need to happen in the US. But this is definitely on our radar. You've probably started hearing about battery integrated appliances, right? These are starting to show up in cooking appliances. We've got a couple of companies putting to market battery integrated cooking ranges and battery integrated cooktops. We've sort of shown those on the right there. And the main idea here is, we're trying to maybe replace a gas cooker with electric cooking, but we don't want to go through the expense and the challenges of running new 240 volt circuits and potentially of incurring a panel upgrade, depending on what our load calculations look like. And so the whole idea is that we can maybe just power the entire cooker on the existing 120 volt receptacle that's used to, power the clock on the gas appliance. So this potentially saves a lot of space and reduces a lot of electrical load. Oddly enough, the electric cooking is like one of the largest loads really in any home. Like their nameplate rating typically is around 12 kilowatts, which would be like 2 or 3 heat pump systems. These new appliances are putting in like 3 to 5 kWh batteries on board, and then they're reducing their power draw from the grid at any moment down to like 1.5 kilowatts, right? Which is, roughly like what a toaster uses. So, very exciting stuff here. These have a big opportunity for drastically reducing that 12 kW load that might show up on our load calculations. In the future, I think we're going to see these battery integrations expanding beyond cooking. It's probably going to get into water heating, HVAC, and other loads. So sort of like emerging technologies. I also wanted to provide a little update on the next NEC iteration. So this is the National Electrical Code. Currently, we're in the 2023 version, and we're almost done with the process of updating the 2026 NEC. And we've been involved in that process quite a bit, trying to get some ideas that are more supportive of sort of affordable home electrification into the electrical code, and particularly for service and feeder load calculations. So, covering some changes there, existing dwelling units. So section 12083. For those who are familiar with the code, you might be thinking it's 22083, but the whole load calculation section is being moved to the first chapter of the code. So for anybody who that has meaning for, now in 2026, that's all going to be moving to chapter 1. So we've got 12083. This is for existing dwelling units. This is when we do sort of an inventory of appliances and equipment, and we sort of add up the nameplates according to some rules. We've gotten some good changes in here. We're simplifying it by eliminating sort of the separate treatment that you might have when adding new HVAC equipment. It's currently in there. What that means is we're going to be able to add new HVAC heat pumps to homes at a 50% rating versus 100% of their nameplate. So sort of like doubling the amount of heat pump that we might be able to add to a home. So a really big effective change there. We've got sort of similar changes in, marginally changing how electric vehicles are accounted for and how central resistance heating is accounted for, dropping it from 100% down to 80%. And then we got sort of the general lighting and receptacle loads reduced from 3 to 2 watts per square foot, largely based on a bunch of data we were able to present showing that, LED lighting in households is prevalent. General service lamps at this point are all LED. And so we've got, big load reductions there. And finally, we added some language to avoid some potential double counting of loads. So big changes there, ability to add a lot of new heat pump, and we've lowered the sort of light and receptacles load. Those are kind of like the big changes that we're going to be seeing in the existing dwelling unit calculation. Now, in a lot of cases, we think we want to use metering data, right? Like we think that the meter demand is probably going to be a lot lower than the estimate we get from that sort of nameplate-based bottom-up method. The problem is that this current section in the code, 22087, a lot of folks interpret it that when you add a new load, you have to add it at 100% of the nameplate rating. And, if you're trying to add a new electric cooker, that's 12 kW, right? So if you, look back at the average demand we saw at the first slide, which was around 11 kW, you add that 12 kW load and you're at capacity, right? That's when you need to do that panel and service upsizing. I think we've made some big changes here. So for starters, when you're using this sort of metered demand method, you're now able to deduct loads that are being removed, right? Let's say you were removing an air conditioner and replacing it with a heat pump. Seems logical that you should be able to deduct the one and then add the other, but that was not the case previously. And we can now sort of treat the loads that we're adding or removing using values and demand factors from elsewhere in the load calculations section. So rather than having to add your new heat pump at 100% of its nameplate rating, we can look back at that section 12083 we were just talking about and instead add it at 50%. And the same goes for if you're adding a new electric cooker, right? Instead of adding it at 12 kW, we can add it at 6 kW. So really big movement there in terms of like how the loads are accounted for when using this metered demand method. And I think this has the potential to, really open up the sort of loads that we're able to safely add to existing dwellings. And then I'll finish up on sort of like the load controls. I think Alex sort of acknowledged that the electrical code already permits sort of like energy management systems through EVs, right, through electric vehicle control. But we've sort of succeeded in expanding that pretty dramatically, I think, for the 2026 code cycle. We now have a new section addressing power control systems, 120.7. And power control systems are going to be sort of replacing the idea of energy management systems for this purpose in the electrical code. And really the main difference is that they have been, a power control system will have been evaluated for sort of safely managing power, for the purpose of this kind of load calculation. Whereas energy management systems, they're not evaluated for their safety or ability to do that. They're evaluated in other ways, but not in this way. And so we've added a lot of content for these PCS systems that reflect common use cases in dwellings. We've added example calculations to Appendix D that like will really clearly lay out the sort of like where the metering is occurring and where the load control is occurring, all to sort of hopefully make this much more helpful to us. And then finally, we've got explicitly the ability to use controls for non-coincidence. So the sort of like circuit sharing, circuit splitting that I'm guessing Alex had talked about. Last slide here. So pulling this all together, like what difference are we making, right? Like if we've got these sort of like advanced technologies that Alex talked about, we've got these sort of like new code provisions that are going to be a little bit friendlier to household existing dwelling electrification. What does it mean? So we built off that res stock analysis I showed, that big map, where we actually tried to electrify every home in the country, and we evaluated how sort of constrained it was for amperage or how constrained it was for physical space, and then tried to actually solve those problems in an automated way, right? Like use the circuit shares, use the circuit splitters, use a smart panel, and find out how many of these sort of replacements can we avoid by using these sort of like optimized approaches and by looking at our next code cycle. So, the long and short of it is by using these kind of least cost technology solutions, plus the 2026 NEC revisions I just described, we're looking at like a 9x reduction in the required panel replacements in US single family homes. So pretty big stuff there. In looking at these plots, we're sort of like, on the vertical axis, we're looking at the 2023 NEC at the top and the 2026 at the bottom. And on the horizontal, we've got sort of like, business as usual electrification on the left, and then sort of optimized electrification on the right. And the pink is showing us, how many panels we think probably need to be replaced. And if we sort of are like at the current, standard practice 2023 code, it's like 56% of the panels in the country need upsizing and replacement. We get a good drop of like 12% fewer panel replacements just from the code changes. And when we sort of like wrap it all together, do the code changes and sort of change, how we design, again, along the lines of what Alex described in a bit more detail, we get down to maybe a number that looks more like 6%, right? So we're looking at the 56 down to 6%. And so that's what we're trying to get get out in front of folks so that we understand what the potential is here and what the scope of the current problem is, and evaluate what these pathways look like for solving them. This is all in simulation land, right? And we're starting to see some good projects and programs that are trying to actually like demonstrate these sort of optimal electrification approaches in actual homes, do the metering, validate Sounds like my time is up. Greatly appreciate your attention. Thanks for the friendly nudge there, Marco.
Thanks, Brennan. Thanks for on behalf of everybody here, and thanks everybody for joining this very interesting discussion about future of electrification. And we'll see you every one of you in the next talk. See you. Bye bye. Thanks, Brennan.
Thank you very much.